Click the bell icon to get latest videos from Ekeeda.
Hello student, welcome back to the subject of Machine Design 1. We are right now working on a numerical on power distribution shaft. In the previous session and previous that session, we have done the force analysis and we have done the resultant bending moment or maximum bending moment calculation, and we have found out that at point D the bending moment is going to be the maximum. Now let us work at the torsional moment. The torsional moment we already have figured out for point C, torsional moment at point D, and torsional moment at point E in our calculations, based on which if you draw the diagram it becomes, for this region it comes out to be 0, for this region it is coming to be like this, and for this region it is coming like this. For rest of the region it is again becoming 0, where it jumps from 0 to the highest value, 0 to this value, and this value to again 0. So let us write down these values and the found out values which are already written there. So we can see at point D we can experience the maximum shear stress again, and therefore extreme loads will act at point D, where we know that the bending moment is equal to and the torsional moment is equal to. So this is the final selection of the values of bending and torsional for the given shaft. Let us move ahead and find out the bending stresses and shear stresses. The formula is very simple and clear also. So it is bending moment and this is your torsional moment. So the value comes out to be Z, in our case comes out to be, whereas the value we have already considered for this is, or we'll keep this in terms of D only for time being, and therefore sigma B value comes out to be this expression, a constant divided by D cube Newton per millimeter square, where D is the unknown value. Let's move ahead for the shear stress calculation. Shear stress induced will be given by this formula, where MT value comes out to be, if we solve this expression ahead, we'll get the shear stress induced is equal to, again in terms of D cube, somewhere around 3039600 Newton per millimeter square. This also is in terms of D cube. So basically unknown factor we have kept as it is, which we are going to substitute in the subsequent equations. Now there comes the nature of stresses. We need to understand that shaft is a member which is going to rotate continuously. So in that case the forces acting on it will, or the forces acting at one point will always get reversed in such a manner. For the case of maximum stress and minimum stress, it is going to be the positive sigma bending and negative sigma bending. When I say positive sigma bending, it is associated for sagging, and when I say it is negative, it is associated with hogging. Whereas the tau max is the only thing that is going to remain constant, because it is irrespective of the direction of rotation, and that's why it remains the T. If we take the mean of this two, it becomes 0, no doubt that, but if we take T mean of this, it remains tau only. So these are two important takeaway from this particular session, which we will be using in further subsequent equations. Let me mention that due to reversed nature, due to rotation. Now from PSG 7.8, and these are important because they are equivalent stresses and equivalent shear stresses. Now the formula is very simple, where it becomes mean and this particular factor. The ratios are already mentioned. For our case, Kf factor is equal to 1.6. It is mentioned in the same page. We have sigma A is equal to sigma B, because which is the bending stress. We have sigma Y is the yield stress, and we have sigma is 0.5 times sigma ultimate. If we substitute back the values, this particular value, mean value, is already 0 in our case. Kf factor is 1.6. Sigma A becomes sigma B, which value we already have written down is 2158.6075 into the yield strength that we already know about it is 370, and this particular factor becomes 0.5 times 650, which is the yield strength. Upon solving, we'll get the value in terms of some constant divided by d cube. Of course, the value remains the same, Newton per millimeter square. The same thing here is done. T mean here is tau only, so the value is in terms of, let me write the value instead of tau, it is 3039,600 plus the Kf factor, and all other things are void because the Ta value is already 0 in our case, so this value particularly becomes 0, so it remains T cube. Let's write down the calculated part. So these are the main takeaway from this, where T equivalent value is given by this particular expression and tau equivalent is given by this particular expression. We know this is the final equation. The ratio between the n factor and all these are given. We already have these values. So after substituting, we'll get, let us square on both sides so that the square root option goes off. So the value of n we have been given is 1.8. Let's make it square, is equal to T sigma equivalent value we have already written down, and it is 37115100 divided by d cube into sigma y option we already have, which is 370, the bracket square, plus tau equivalent value we have figured out is 3039,600 divided by d cube into tau y is basically given by this particular formula, so which is 370 divided by cube root. After evaluating, the only factor is d cube raised to 2 that we get, and therefore it becomes d raised to 6. I've already figured out this calculation, you can work out with this, and that comes out to be somewhere around 3346564753 millimeter raised to 6, and if we take the 6th root, we will get the value of d somewhere equal to 38.67 millimeter. Now again, it is not the perfect value of the diameter, so let us go for the preferred value, and therefore let us say d is equal to 40 millimeter. Which is the final calculation of your diameter. So there we had started with the combined loading, then we went for the force analysis on individual mounting, that was gear and 2 pulleys. In the next section, we had looked at the force analysis in horizontal plane, vertical plane, and then we went for the resultant forces, and at the end we went through the calculation for the equivalent forces in bending and in torsion or shear, and then we found out the preferred diameter. So 40 diameter of shaft is preferred for this particular given case, and which will be safe in both shear as well as in bending. Thank you so much for watching this video. If you like this video, please subscribe to Ekeeda. Thank you.